What are the ways that matter can interact, and what kind of physics do we need to describe those interactions? I'm going to suggest three broad classes of interaction. Long-range interactions occur between objects without even touching each other. Short-range interactions, we'll consider that when objects do touch each other. And macroscopic objects, such as this pachyderm right here, composed of zillions of atoms, they experience these classes of interactions all the time. And those interactions can be well described by classical mechanics. However, down on the microscopic scale, or the nanoscale, with interactions between individual electrons, protons, atoms, molecules, those interactions require quantum mechanics to describe them. So, of course, classical mechanics we need to describe interactions between big things, and quantum mechanics for small things. Let's look at examples of each of these three classes of interactions. Long-range interactions, most obvious of which is gravity. The Earth and the Moon can interact with each other even though they never touch. Over great distances, they're still exerting forces, a force of gravity on each other. The second example of a long-range non-contact interaction would be an electric force, electric interactions between charged objects. If we take this orange balloon and rub it on Sir Isaac Newton's long, flowing, powdered hair metal locks, and then separate them, we'll see his hair lift up and be attracted towards the balloon. Because his hair has become positively charged, the balloon is now negatively charged. And even though they're not touching anymore, they are still interacting. There's a long-range interaction, this electric attraction between them. Electric forces can also produce repulsion as well, unlike gravity, which is always and only attractive. The third kind of long-range force is that due to magnetism. Here is a bar magnet with a north pole that's marked. I'll bring in another bar magnet here, and we can see them interact without even touching. There we go. Magnetism occurs over long ranges. Let's switch to looking at short-range interactions. The very most common would just be straight-up contact forces between solid bodies. Here's a solid object, that magnet once again. Here's another solid object, this hammerhead shark. There's no long-range interaction between them. They can't interact without touching, but if they do actually touch, then I can push the shark with the magnet, and I can push the magnet with the shark. Those are contact forces between solid bodies. What about forces between solids and fluids? A fluid can mean a liquid or a gas. And these four phenomena we observe: drag, pressure, lift, and buoyancy. Pressure we see whenever you drop a solid into a fluid, like if we drop Sir Isaac Newton into the bottom of this swimming pool and see his hair drifting around. The water pressure pushing on him from all directions, that's an interaction between the water, the fluid, and this solid, Newton. These other three we can see examples of here. Drag is an interaction between a solid, this meteor, and the surrounding air. Buoyancy is an interaction between this solid, the hot air balloon, and the surrounding air. If the density of this solid is less than the density of the surrounding air, then we get buoyancy, we get lift. That's an interaction. And then here, this solid, this airplane, has airfoils over which air flows, so an interaction between the solid airplane and the surrounding air gives lift on the wings. Those are all interactions between a solid and a fluid. What about interactions within a fluid itself, between a fluid and a fluid? Internal interactions between parts of a fluid. Imagine here, this is a hose carrying oil, maybe pumping oil through part of an engine. Oil is coming in here, flowing through, coming out there. We can see pressure and viscosity inside the fluid itself. Imagine that this blue piece is a bit of oil next to some neighboring bit of oil, this pink piece here. The blue oil is going to be pushing forward on the pink oil. Likewise, the pink oil will be pushing backward on the blue oil. That's pressure, neighboring bits of fluid pushing away from each other. Then over here, maybe if the pink starts to overtake the blue, this pink oil moves up this way faster, then those two neighboring parts of fluid could rub against each other like this, creating a kind of internal friction that we call viscosity. That's going to cause the fluid to heat up. So these are two main interactions we see inside a fluid itself. How about interactions between parts of a solid? interactions inside a solid body. Pressure, tension, and internal friction are all examples. Let's say here, if we look into the Earth, here's the Earth's interior here, all this rock layered on top of rock, all this solids in contact with other solids. So a little bit of rock inside here, this region is being pushed upon by all the surrounding rock. It's feeling pressure inside the solid body. It's one part of a solid pushing on another part of a solid. Pressure there as well. Tension will occur in a rope or cable or string, anything that is stretched out, anything that's being stretched and held stretched, a spring perhaps. Here we've got a box of llamas that is being suspended by a rope from the ceiling. And this rope, of course, will have tension in it. What does that mean? If we zoom in on a little section of the rope here and say this little, we'll color this section of rope blue and the little section beneath it pink, the blue bit of rope, it has to pull upwards on the pink bit of rope. The blue rope is holding up the pink bit. Likewise, the pink bit of rope is pulling down on the blue bit of rope. So we call this pair of interactions tension. It's kind of the opposite of pressure up here. Here, pressure is when two neighboring pieces push away from each other. Here, tension is when two neighboring parts of a solid are pulling towards each other. Lastly, internal friction. Let's say we've got a spring here, a solid spring that we are stretching out. Grab this spring and stretch it out. The metal expands, stretches, and as that happens, bits of metal neighboring each other, like this little blue bit of metal neighboring this little pink bit of metal, they might move against each other like this as the metal expands and stretches and changes shape. There we get an internal friction that's going to generate heat, very much like viscosity inside a fluid. Internal friction inside a solid itself. That covers our short-range interactions, our touch interactions, and that's the end of what we can describe with classical mechanics. So let's switch over to looking at what we can describe with quantum mechanics. Microscopic interactions down on the nanoscale. Chemical reactions fall into this category, of course. That is rearrangements of electrons between atoms and between and within molecules. Heat transfer. We really need quantum mechanics to describe heat transfer because this is a phenomenon that's occurring as a result of microscopic collisions between air molecules transferring heat from this hot gas to the surrounding air. We really need quantum mechanics, or at the very least statistical mechanics, to describe heat transfer properly. Third and finally is interactions between matter and light. We have to have quantum mechanics to really describe this. A photon approaches some atom, the atom absorbs the photon, the electron jumps up to a higher orbital, holds that energy for a while, then de-excites and re-emits that photon. This is a fundamentally quantum mechanical interaction here and has no analog up on the macroscopic scale. That covers our microscopic interactions, and to conclude, we're going to be focusing mainly on these macro scale interactions here.